Welcome, everybody. This is a talk that I really enjoy giving. It's on Lambda Calculus. And I really wanted it to be a talk that is both an introduction and a fun introduction to Lambda Calculus, but also doesn't shy away from all of the academic jargon and language that people use to describe Lambda Calculus. I made this talk while I was teaching for a company called Full Stack Academy here in New York. I currently work for Google, but this is not a Google-based presentation. This predates it, and it's entirely my own opinions. One sec, I'm going to turn off my notifications. And I'm really happy today to be joining the first FrontSide conference. So let's just dive straight in. And we'll do so with this function called identity. So let's take a look. We're going to define, I'm going to use some typical JavaScript stuff. I'm here in a node REPL, so I can do mathematical expressions. I can console log some things. And I can do anything you might expect out of JavaScript, such as mapping a number to one more. And we can see 2, 3, 4. OK, so what about this thing on the screen? I'm going to say that this function called identity, or I, is the result of taking a value and returning the same value. This is a very simple function. So you can all imagine that if I do the identity of some value, we get back the same value, regardless of its data type. And very importantly, I can do the identity of identity. And as you might expect, since this function returns whatever I give it, I get back the function identity. All right. So we saw that identity was defined as a function, and I'm going to use this little lambda to signify a function that takes an input and returns the same input. So the identity of any x for any and all x is always going to be x, and the identity of identity is identity. And right off the bat, we're seeing something really interesting here, which is that functions in this universe are nouns. They can be passed to other functions and returned from functions. As JavaScript developers or developers in other languages with first-class functions, this is probably pretty familiar. In Haskell, which is a language that I really enjoy, this is called the ID function. And it is given to you along with a lot of other pre-built functions in the package base, specifically in the subsection of base called Prelude, which every Haskell program implicitly imports by default. You can turn that off, but by default, every Haskell program gives you this ID function for free. So I flashed a bunch of stuff on the screen in different colors and different places. What is this business with this symbol lambda? So for a given expression like this, the lambda is going to be my notation to define a function. It's going to be like the fat arrow in JavaScript, or def fun in some languages, or function in the old style JavaScript, and all sorts of things like that. And it takes an input, a parameter, and it returns some expression. So it's just a mapping from input to output, and it has the very fancy name of lambda abstraction. These things show up all over the place now. They're pretty familiar to most of us, I think. In lots of different languages, they have all sorts of different syntax. But in the lambda calculus per se, we use this little lambda symbol to signify we're starting the definition of a lambda, or a function that takes inputs and returns outputs. Now, this language that we call lambda calculus has a very small syntax. It has variables, which are boring. It has the application of some expression to another expression, which is function application, and that's signified just by a space in between things. So in lambda calculus, we don't use parentheses to invoke functions. We just put the function in front of the thing it's operating on. And we can define functions, which we call abstraction, and we use the lambda notation and a dot to do that, input to output. And then finally, depending on how you set up your grammar, you can use parentheses to do grouping, so you disambiguate ambiguous expressions and you know what you're talking about. And this is it. This is all of Lambda Calculus in a single slide, all of the syntax in any respect. So the rest of this, we're going to show JavaScript versus Lambda Calculus, compare and contrast, and see how it plays out. So we've got these variables, and that's kind of it. In Lambda Calculus, variables are somewhat boring in that they don't actually mean anything. They mean whatever you want them to mean. The only important thing about them is once you know what the definition of a variable is, or you've stated what x is equal to, it never gets reassigned. There's no mutation in Lambda Calculus. X is like a variable in math. Once you know what x is, you know what it is, and it's not something else. I mentioned function application. So function application in Lambda Calculus is just f operating on a. We don't need to use parentheses. The parentheses are implied or just not part of the grammar. And if we have multiple inputs like a and b, that really means successive invocations. So f of a is itself a function, and the fa function is operating on b. And we'll talk more about that in a little bit. We can use parentheses to make this clearer. We can put parentheses around the first expression. And now we're making it very obvious that f of a is some kind of value. Maybe it returns a function called g. And g is what's operating on b. But most of the time, we just leave off those parentheses. We say function application in Lambda Calculus is left associative, which means we can put parens around the left side and we can keep stacking them up. But most of the time, we just ignore that. On the other hand, if I put parentheses around the right hand of this expression, now I'm talking about something different. Now I'm saying call f on the result of a applied to b. So a gets invoked with b, that returns some new value x, and f is being called on x. So that is a very different expression from the previous one. And there, I do need the parentheses if that's what I intend. So, whoops, that is function application in a nutshell. And we're going to see this a bunch of times. So if you're still a little fuzzy on it, just remember that it's the same thing as normal function application, except we just don't use parentheses unless we absolutely need to. And I mentioned defining functions, Lambda abstractions. So these are inputs to outputs. In JavaScript, we might use a fat arrow function to denote that. But in Lambda Calculus, we say a lambda starts a function definition, and the dot separates the input from the output. If I put more stuff to the right, the body of the lambda abstraction, by convention, is everything to the right of the period, everything to the right of the dot. So here, this means take an input A and return, that's that dot, B applied to X. This entire expression is the output of this function. And I can make that clearer, again, using parentheses. So we could say A returns B called on X, but by convention, we know that everything to the right of the dot is included, so we just don't put those parentheses. We can if we want to, we just tend to not to. On the other hand, if I put parentheses around the left side of this expression, breaking up that right-hand side, now I'm talking about a very different expression. Now I'm saying, take the function that takes in A and returns B, this function here, and call it or apply it to the value X, which is different from what we did before. Before we took in an A and we returned B of X. Now we're taking an A to B function and calling it on just X. So there, I do need the parens if that's what I want to mean. And finally, notice that functions are allowed to themselves return functions. So here we are saying, take an input A and return, that's the period, everything to the right of the dot, which is a new function, B returning A. Take an A and return a B to A function. So again, everything to the right of the dot is the return expression. And if we wanted to, we could put that in parentheses to make it clearer. but by convention, we don't. Okay, lots of syntax. I promise you, this is not all a big, dry academic presentation about syntax. There is actually stuff to learn here that is interesting, but you can start to get a feel for how lambdas and arrows are the same thing, just with the lambda comes at the front instead of the arrow goes in between. And so once you get practice with that, you get kind of comfortable with it and you can just move on with your life. Here is the most dense symbological slide of the whole thing. This is called beta reduction, and it is the action of simplifying an algebraic expression. Just like in school, when we're learning how to take some math expression and keep applying operations until we get a final result, we're going to do the same thing here, and we're going to reduce this reducible expression. So how does this work? Well, we could see we have a function here in red that takes an input and returns the same input. And that function is being applied to everything to the right. It's being applied to this expression here. So that expression is going to come into our function as the input A. And now we go look inside the function body for every A variable, and we do variable substitution, every instance of A with this argument, the BCB function. And that is our first simplification step. Take this big value, BCB, put it into A, and replace all the A's. And that eliminates this lambda. We took a function, we called it an argument, and it returns a value. And this is the value. So now we just keep going. We have a function in red, and we have an argument in blue. We're going to take that argument, pass it into our function as the B parameter. And now we do the same thing we've done a million times in our programming languages. We go look inside the function body for everywhere that parameter exists, and we substitute it for our argument. X comes in as B, it replaces all the B's in the body, and we get this result as our simplification. Once again, we have a function in red. We have an argument in blue. It's going to come into this function as the parameter C. So this EF value, that replaces all the C's in the body of this function. This function doesn't have any C's in the body, so the simplification here is trivial. We just return X, whatever that might be. There's nothing left to do here. We just have an X sitting on its own and no way of simplifying it. We don't even know what X is. It's just a symbol. So that's it, we're done. We call this beta normal form and this process beta reduction, but it really just means applying a function to an argument and simplifying the result. Doing algebra, that's all it is, symbol manipulation. Now, there are some caveats. Depending on if you could do multiple simplifications, which one you choose first can either send you into an infinite loop or maybe get you an answer, or maybe send you into an infinite loop. So there are some tricks to which one you do first. And sometimes doing one first is faster than doing the other. The other thing is if you have a bunch of variable names and some of them are accidentally the same name, you have to be careful not to mix up those variables. And there are algorithms to actually avoid that. The easiest algorithm, by the way, is just rename all of the variables to be unique. But we're not going to go into that today. The thing I really want to focus on here is that this is the same thing we've all done a million times in our programming, which is to pass values into parameters and do variable substitution. Okay, so let's see that in action again with a new function called the Mockingbird. Mockingbird takes in an f, some parameter, and it returns the result of calling f on itself. So there it is in JavaScript. That's the M function or Mockingbird. And we can try this. We could say, well, what happens if we call a Mockingbird on the identity function? Think about it for a second. The I function, that was that function that returns whatever we give it, is coming in as its input, and then it is being called on itself. So we get an identity of identity, which we've seen before, and the answer there was identity. Okay, so it takes a function, calls the function on itself. And that's really interesting because what happens when you call the mockingbird on the mockingbird? So this M is our input. It's the F here. That's what it's bound to. And we return M applied to M. Okay, so the result of this expression is take M and call M on M. But wait, we still have work to do. This can keep simplifying. So we take the M function and we pass it into M, which means we take M and we call it on itself. So that's equal to, you see what I see? We're back into an infinite loop. And that's really interesting because this means that this is getting close to what we call the halting problem. It's getting close to all sorts of problems with computability, which we're going to talk about. And this expression is called sometimes the omega combinator because it just keeps going on until infinity. And if you try to run it in JavaScript, you do indeed get the mockingbird of the mockingbird is the mockingbird of the mockingbird, which is the mockingbird of the mockingbird, which is a call stack size exceeded because JavaScript doesn't have tail recursion. At least not all engines do. And unfortunately, this is a call stack explosion. Okay, so there's one more bit of syntax that I want to show you, and it is a shorthand. I mentioned that we can have a function like this one that returns functions. So this function here, this arrow, which is this first lambda, if you give it an A, it returns this function that takes a B and returns a C to B function, etc. That can be expressed using these nested lambdas, but for a shorthand, for convenience, we like to condense all the nested lambdas and just write a single one. So a function that returns a function that takes a B, that returns a function that takes a C, we just write that as lambda ABC. It's the same exact meaning. We have not changed the meaning of what we're dealing with. This is still a function that returns a function that returns a function that returns a value. So it is not a function that takes 3 inputs all at once. We're not doing this style. It is just a way of writing it differently. And we'll see that in action here. This is the same example as before, except now our BCB function here has been condensed down using this lambda syntax. So once again, we have a function, we have an argument. The argument comes in as the parameter. We go replace the A's in this function body with this BCB function. And that's our first step. Now again, we have a function and we have a value. That value comes in as the parameter B. And this time, this is where this syntax shorthand comes into play. Since we have 2 inputs here, that really means nested functions. So the body for this is everything to the right of the first parameter. And this, even though we haven't written it, it has a little lambda there stuck inside it that we hid. We made it secret, but it pops back out as soon as we do this simplification. This function takes a B and returns this C to X function. And then the rest of this is exactly as before. This EF function comes in as C. We go replace all the C's in the body. There are no C's. We end up with X. We have the same result. Just wanted to make it clear that when we have multiple inputs, that really means a function that returns another function. And we call this currying. So let's look at currying quickly here. This is what it looks like. This is a sort of classic example of currying. We'll make an add function that takes an I and a j, and it returns I plus j. So it does not take I and j simultaneously and return I plus j. If we did it that way, then anytime we call add, we would have to pass in both values. That works, but if we don't pass in all the values, we instead get garbage. It can't handle it. This is an inflexible function. This style of function demands that you give it all of its inputs now, otherwise it quits. But we want to do something more flexible. So this is a curried function. It is a function that takes a single parameter and returns a function that takes a single parameter, which returns an expression. And now we can call it with one argument and then the result with the second argument. And we get our final value. So we can still do everything we did before. We can still pass both values in because if we have them, we can use them. But we gain a new superpower. We don't have to call it with all of its parameters. If I just give this a single argument, I get back a function. And there it is. It just says function. So if I store this function as something like increment equals add 1, I now have a reference to this returned nested function, and I can pass in new values to it. So if I increment 8, I get, a typo. If I increment 8, I get 9. If I increment 3, I get 4. And we could do the same thing. You could say multiply takes an I and a j and it returns I times j. And now I could say double equals multiply by 2, triple equals multiply by 3. If I double 7, I get 14. If I triple 9, I get 27. And so because these new functions, these curried functions, these nested functions, are flexible enough that they don't need all of their inputs. They can just get one at a time. That lets me take a general function like mult and create specialized, customized versions that have closure with one of the arguments fixed. I'm creating new functions that are purpose-built from my function builder. And that ends up being one of the secrets of Lambda Calculus. Cool. Let's see another example. This one is the kestrel, which I will name K. It takes an A and a B, and it returns A. So I can apply it to two different things, 1 and 2. And if I pass this in, 1 will be bound to A, 2 will be bound to B, and I return the first thing. If I call it with 2 and 1, it's going to return the first argument, which is a 2. If I call it with other functions like m and I, I'm going to return the first one. So it always returns the first thing. Here it is again. We saw it takes an A, it takes a B, it returns A. Very good. So now we could say the kestrel of the mockingbird and the identity is, and you should be filling it in your own mind now, the first thing, which is M. Or the kestrel of I and M is always going to be the first argument, so it's I. And in Haskell, this function is given to you as a function called const. Const in Haskell is not a variable definition keyword. It is a function, and it is not used for variable definition the way you would do it in JavaScript or something. It's a completely different function, just with a similar name. But why is it called const? It takes two things and returns the first one. So const is funny, like why not first? Well, let's see an example. I'm going to do that a million times. There we go. So this k function or this const function, remember it's curried. So I don't have to give it two things. I can, and then it always gives me the first one. But I can also just give it one argument. Remember that returns a function, the k1 function. And now this function, no matter what I pass it, it always returns that thing I put into it, 1. So this is a function that is obsessed with 1. The km function is a function that is obsessed with the mockingbird. If I call it with I, it returns M. If I call it with M, it returns M. If I call it with K, it returns M. So you could see now why this thing is called const. It creates a function that all that function ever does is return a single primitive constant value. Okay, we're starting to get into the fun stuff here. I think all of it's fun, but we're really starting to hit some flexible, usable tools. And this is an interesting one. What if we call k on I and x? Now remember, k, the kestrel, is the function that if you give it two things, returns the first value. So we're going to call k on I and x, which means the result of this, you should fill in, is I. Okay? But this equality here is not quite the same as a programming language return statement. It's not mechanical where we only go left to right. This is like algebra. This equals sign literally means these are the same thing on either side. And since I is a function, that means k of I and x is a function. It's the I function. And since that thing is a function, we can call it on some new value y. We see how we do that? These two sides are identical, so we can put a y after them, and they're still identical. Well, we know what the identity of y is. The identity of y is y. So not only is this identical to this, and this identical to this, but because equality is transitive, this is identical to y. Calling k of I and x and y returns y. Let's try it just to convince ourselves. K of I, and we'll do 1 and 2. Actually, let's do m and k. So k of I and two things returns the second one. So this is going to return k, or I could do 1 and 2, and it returns 2, or I can do x and y, and it returns y. All right. So suddenly, there we go. Oh my gosh, go away. There we go. Suddenly we have something new. We have something we didn't have before, which is this function here, k of I. If I pass it two inputs, it returns the second one. Remember, k, if I gave it two inputs, returned the first one. But k of I, given two inputs, returns the second. And we've just invented a brand new function called the kite. The kite is the result of calling k on I, and the kite is the flip of the kestrel. If the kestrel takes two things and returns the first, the kite takes two things and returns the second. And notice that in order to create this new function, a brand new function with new behavior we've never seen before, I didn't have to use my function definition keyword. I didn't have to write a lambda. I just called one function on another function, and boom, a brand new function with new behavior popped out that we've never seen before. That is really exciting because it means that in order to create new functions, we don't necessarily have to write down their implementation. We just have to combine things. Now, we can do it the manual way. We can do it the way we've been doing this whole time. We could say ki is a function which takes in an a, and it takes in a b, and it returns the second one. And that will work the exact same way. So now we can call it with two things and it returns a second. So we could still define the ki function by hand. But I really want to get at how exciting it is that we don't have to, that we can define ki simply by passing k and I and gluing them together, and that gives us this brand new behavior. That's really cool, because getting new stuff just by combining old stuff, that's the essence of functional programming. That's the essence of combinatorial logic. Let's see it in action just a couple billion more times to make sure we're all really on board with this. K of I on M and K takes two things, returns the second. So the result here is K. It's the second one. K of I on K and M, well, always returns the second one, so we get M. So between the kestrel and the kite, we have these two different functions, which are kind of the flip of each other. And by now, some of you maybe are wondering, why are there all these birds in this presentation? Why is this called a flock of functions? Well, let's take a look. We have a brief little bit of history here, which is this mathematician named Schönfinkel, and I can't pronounce German, so I apologize for that. And he came up with all of these long names for functions. Things like Identitätsfunction and Zusammensetzungsfunction. Haskell B. Curry, who came a little later, also did a lot of work with these functions. And he used some of the same letters, but he also used a couple different ones just to confuse everyone. And then even later, this logician and puzzle author named Raymond Smullyan wrote a book called To Mock a Mockingbird, which is really delightful, quite challenging at times. It's sort of a game and puzzle book, but it is about these functions. And he used as a metaphor birds in a forest instead of functions in a domain. And so he gave all these variable names like the kestrel and the cardinal and the bluebird and other bird names in English. I don't know why he didn't use the ibis. He used the idiot, which is whatever. We won't go there. Now, he didn't just pick these birds completely arbitrarily. He actually was honoring Haskell Curry, who was known to be an avid bird watcher. And this should also ring some bells. You're hearing the same Haskell Curry, and I talk about curried functions and the Haskell programming language. So who's this guy and why does he matter? And now we're going to go into a little bit of history. I'm going to fly through this in the interest of time, just to give you the flavor of what's going on here. But around the late 1800s through early to mid 1900s, there was a huge revolution in mathematics where people were really digging much deeper than they ever had into what is mathematics? What is the nature of it, the philosophy of it? How do we tell whether certain things can be computed, whether certain answers can be achieved? So people were trying to find a unified theory of math, much like a grand unified theory of physics or something like that. So I first want to talk about Peano. Giuseppe Peano in 1889 starts creating this formal notation for functions. And he also invents these things called Peano numbers, where he defines the natural numbers as there's a thing called zero, and there's the thing that comes after zero, and there's the thing that comes after the thing that comes after zero, and so on and so forth. And that's how he defines numbers. Shortly after, Frege does a lot of work with axiomatic logic and his own function notation, which is based on sort of graphs and trees. And he uses a form of currying at the time, functions that return functions. In 1900s, Russell and Bertrand write Principia Mathematica, an attempt to unify all of math. And in the process, actually a little earlier, Russell found a paradox. He found a paradox set theory, which was the question of, does the set which contain all sets that do not contain themselves, is that set in itself or not? And if you follow that logic or try to follow that logic, you can't answer it. It goes back and forth. So we needed to rewrite the definition of sets to avoid that paradox. But that was the first crack in the foundation of math, where people realized that things they'd taken for granted maybe weren't as simple as they thought. Finally, the early stage, we get to Schonfinkel, who I mentioned, who does a ton of work on combinatory logic. The idea of these functions that if you pass them into each other, they give birth to new functions. And these, k and I and m variables and things like that. And he also uses currying extensively. Now, he has a very short and brilliant career. I think it's like one paper or something like that, maybe more. But sadly, his life is a bit tragic, and you can go read about it. And so it's cut short. I'm going to mention John von Neumann here because he also sort of by accident invented a functional system of set theory. That wasn't really what his goal was. He wasn't trying to focus on functions, but he ended up doing some important work there. Later, he did a ton of very important work on the first physical computers. And then we get to Haskell Curry. So this is a logician who goes and studies in Germany. And he studies combinatory logic and does a lot of contributions. And then in 1927, he discovers Schonfinkel's work and realizes Schoenfinkel already discovered a lot of what he'd been working on, but not everything. And he goes on and continues to do a lot of important work in combinators. Then we get to Gödel, and Gödel, unfortunately, is the one who really is the assassin of mathematics. He discovers that this whole endeavor, this journey to try and find a grand unified single theory of math, the axioms that will give rise to everything, is fundamentally flawed. It is literally impossible that any system complex enough to express piano arithmetic, any system interesting enough to express piano arithmetic, will either be incomplete or inconsistent, meaning you will not be able to prove some things in that language, or you'll run into contradictions. That is such a thorough destruction of the idea of math up until that point that many people violently disagree with it. And it takes a while before people become convinced, but they do become convinced. And it turns out that every mathematical system, you pick some axioms, you see where it leads, but there's no one version of math. Okay. In addition, Gödel does a lot of work on something called recursive function theory in an effort to see his version of what's a general version of the most broad definition of math. And in addition, we have Rosa Peter, who's also known as the mother of recursion theory. She writes in 1932, Recursive Funktionen, and does a lot of great work there. And now we have Alonzo Church. And Alonzo Church, working in Princeton, also trying to do what everyone else on this page is doing, which is find a unified single theory of math that can express everything, invents this thing called Lambda Calculus, this tiny little language that we showed the entire syntax for already, which can model computation. Computation meaning some sort of step-by-step process by which things can be solved. There's a more formal definition, of course. But he uses this to answer a very important question of the time, which was David Hilbert's decision problem. This was a previously unsolved problem which asked, for any kind of computation or calculation, can you write a program that tells you whether that calculation, that expression, can have a final answer? It's very closely related to the halting problem. Can you write a program that if you give it any problem, it'll tell you that the problem is solvable or not? And the answer is no, you cannot write such a program. It is impossible. And he uses the Lambda calculus, his invention, his little formal theory, formal language, formal system, to prove that. Which is a giant result at the time. This is a years-long unanswered question. And he's answering a fundamental philosophical question about the nature of mathematics using everything that we've shown you so far. He has some grad students who are also famous, like Stephen Kleene, who goes on to invent regular expressions and do a lot of work with important stuff related to computers. Berkeley Rosser. So they help him discover all sorts of versions of Lambda calculus. And there's a whole thing called the Lambda cube, which has different Lambda systems. And we're not going to go into it, but they do a lot of important work too. And so, yeah, Church in 1936 solves this unanswered question. Now, in the same year, Alan Turing, who I think we're all very familiar with, also solves the decision problem. And he solves it and writes a paper using something called Turing machines. We call them Turing machines. And he actually came a couple months after Church. And then he found that out, and he was somewhat disappointed about that. But he was also excited because he took a very close look at his Turing machines and Alonzo Church's Lambda calculus. And he thought to himself, you know what? These are the same thing. I can write in my my Turing machines a machine to compute Lambda calculus. And therefore, Turing machines are just as powerful as Lambda calculus. And I could take Lambda calculus and simulate a Turing machine with it. So Lambda calculus is just as powerful as Turing machines. So they're both equally powerful, meaning they can both do everything the other one can do, which means they're the same thing. They are both systems for modeling computation that are equally powerful. Anything you could do with one, you can do with the other. That's a really exciting result. And not only does he show this, but he also shows that general recursive function theory is the same thing too, that all three of them seem to have accidentally, independently landed on a way of modeling computation that is actually identical in terms of what it can represent and model. So this sort of suggests, and this is what's known as the Church-Turing thesis, this kind of indirectly, subjectively suggests that that model of computation that all three of these things surface is sort of some kind of underlying version of reality, mathematical reality, that is interesting and useful. So anyway, he actually goes to Princeton, studies under Church, publishes the first fixed point combinator, does a lot of other things. Okay, so combinator. I've said this word a bunch. I talked about the K combinator and the M combinator, or I've written it on the screen. And I'll just quickly define what a combinator is. It's a function that all it does is remix its arguments. It doesn't use anything outside from like other syntax or globals or whatever. It just remixes arguments. So this is a function that takes an input B and returns B. So that's a combinator. This function, on the other hand, returns A, but A is not an input to the function. So this is not a combinator. This is a combinator. It takes two inputs and it returns the first one. The fact that it doesn't use one of the inputs, it doesn't matter. The only important thing is that this return expression, this came from an input. Conversely, this is not a combinator because this B value, we haven't defined it anywhere. It comes from outside the function. It's something not part of this function. So it's not a remix of its inputs. It's something else. And even complex stuff like this is a combinator because everything in the return expression, like this C value and this B value, came from an input. Remember, E is an input itself, so that's not important. That's not part of the definition. But C and B, and this thing that like this thing returns, it can summon stuff out of thin air. It's defining a thing in line. That's fair. But it's not using any values that came from outer space. Okay, not super important, just trying to make it clear what combinators are. But we've seen a bunch of these already. I is a combinator, K is a combinator, Ki is a combinator. All of these things, part of why we call them combinators is because of that combination thing I showed you before. When we use K on I, they combine into a new function Ki that has different behavior. So this is really cool. These individual atoms combine into molecules. Let's see a new one, cardinal. Look at this beautiful function. We have three inputs and we have some output expression. And what we do, wrong button, there we go. C takes an F, A, and B, and it calls F, it applies F to B and A. So it takes a function and two values, and it calls the function on the two values, but flipped around. Interesting. So what does that mean? Well, let's try it. Taking this C combinator, a function and two values, we're going to call the function K. Sorry, we're going to call the function K, and we're going to call it on two values, I and M. Well, we know K is the function that returns the first thing. So K of I and M should return I. But the C combinator flips K around. It puts the two values, I and M, into this function K backwards. So it puts M in first and I in second. So the result of this is M. So flip the kestrel or the K function, and you get a function that returns its second argument, which means it's the same as the Ki function. The flip of the kestrel is the kite. That's kind of cool. This cardinal function reverses function arguments. It flips them around. And in fact, in Haskell, we call it flip, and that's one of the built-in functions. Let's try it. Let's make sure this actually works. If we flip the kestrel, normally the kestrel gives you the first thing, but the flip of the kestrel gives you the second thing. If we flip the kite, normally the kite gives you the second thing, but the flip of the kite gives you the first thing. And of course, this works if we define the kite in line. If we flip the kite normally gives you the second thing, but the flip of the kite gives you the first thing. All working out. So what? Why do we care? Like, this is cute and all, but what is the moral? What is the exciting part? Well, remember Turing proved that Lambda Calculus and Turing machines are equally powerful. Anything one can do, the other can do. Turing machines, though, became super exciting. Everyone loved them because if this hypothetical machine can do computation, well, why don't we just build a real one? So we did. We called them computers. And they're a little more complicated. They've got like the von Neumann architecture and things like that. But what do? We shuffle around information by mutating state and moving it in place to place in memory. And that's really what a Turing machine is. It just like reads instructions and writes instructions. And we can program this thing very low level with machine code and say, literally go to that memory and change these bits. But then it's really annoying to write a sequence of on-off switches to do that, like ones and zeros. So we designed this assembly language, which has a little bit more abstract, still one-to-one with machine code, but now we're using text instead. And then we decide, you know what? One-to-one with machine code is still thinking too much in terms of how the machine works, which is very complicated and very difficult. So what if we wrote these high-level things like loop or subroutine call or other kind of like nice high-level structures, whiles and fors and do whiles and things like that, and if else and so on and so forth. And those things we could compile them into machine language, but they would be higher level like C. But they would still be focused on the way the machine works, like C. And then other people are like, oh, you know, thinking about the way the machine works is still too hard. What if we can make more abstract languages like JavaScript or Python, where we don't think as much about the machine shuffling bits around? So we start to get a little bit more abstract, but we still have state. We're still mutating memory, and the semantics of our programs are still organized around that concept, even if we're no longer thinking about individual registers. So then we go even further and we get even more abstract and we say, maybe we can write a programming language where we don't have to think about the machine at all. We just think about our concepts and our desires and our wants from a human perspective. And guess what? The more abstract we've gone, the farther away from the machine we've gone, the more we've started to go towards a pure mathematical way of reasoning about programs. And now, instead of starting from the lowest level, most machine-oriented programming language, what if we did the opposite? What if we started from a system that we know is just as powerful, that can compute everything computable? So we know it's powerful enough, but we don't have any concept of a machine. This has nothing to do with machines. And then we try to go the other direction. We try to use that and make it work on a machine. So we can compile this language down to machine code. We can take this mathematical concept and turn it back into shuffle bits around. And that's called a purely functional programming language. And it is at the heart of purely functional programming languages is Lambda Calculus. Just like at the heart of stateful programming languages is Turing machines. That's the similar metaphor here. So a big moral of this is everything can be functions, literally everything. Now, I really want to be careful here. This does not mean that in functional programming, literally everything is or should be functions, but quite a lot of it is. There are a lot of functions in functional programming. Not everything, but a lot. So everything can be functions. Like what? What can be functions? What are we talking about? Well, what about Booleans? How are we going to do this? In JavaScript, we might say like not x is equal to this Boolean expression of y or a and z or something like that. But in Lambda Calculus, we don't have a not function or keyword or operator. We don't have or and syntax. That's not part of that language, remember? We just have functions. We don't even have equals. We can't test for equality. That was, we wrote down that these things are equal as like an algebra statement, but we don't have like a process that tells us whether two things are equal. We don't have an algorithm that spits out true and false. In fact, we don't even have values called true and false. All we have is parentheses. So how on earth are we going to invent Booleans and Boolean logic just from functions? Let's see. So what is a Boolean even used for? Like, why do you care if something's true or false? The answer is, depending on whether it's true or false, you're going to do one thing or you're going to do a different thing. In fact, we have this in JavaScript. It's called a ternary operator, and we use the Boolean for selection. If something is true, return the first expression. If something is false, return the second expression. One sec. So that's a use case for Booleans. Select either the first thing or the second thing, depending on whether I have true or false. So what's this going to look like in Lambda Calculus? Well, we don't have question marks and colons in Lambda Calculus, so those got to go. But what are we left with? We're left with a thing and a space and a thing and a space and a thing. Well, that's allowed in Lambda Calculus, and that means that this thing is a function, right? We're applying a function to two arguments. So if it's the true function, we want it to return the first thing. And if it's the false function, we want it to return the second thing. Depending on which function this is, true or false, we want to return either the first or second thing. We've already invented that. The kestrel can stand for true and the kite can stand for false. Just like 1 or 0 stands for true or false, or T and F stand for true or false, or on or off stand for true or false, kestrel and kite will stand for true and false. They'll represent true and false, but in a way that's usable. Let's try it out. So I'm going to say that true, whenever I talk about true, I'm really talking about the kestrel. Whenever I talk about false, I'm really talking about the kite. And I'm going to define the kite so that it remembers its name. False is the kite. Good. So true, kestrel, false. I messed up. False kite. Try that one more time. True is the kestrel, false is the kite. Good. We're good. So these are just going to be an alias. This is going to be a variable name that stands for one thing and the other, right? Just like T stands for true. And I'm going to have some bool. So we'll call this some bool. And if you didn't know what it was, you didn't see that, you'd be like, well, what's some bool? If it's true, give me back hello. And if some bool is false, give me back goodbye. Just like a ternary operator in JavaScript. Some bool, question mark, hello, colon, goodbye. Well, since some bool is the true, it's going to give me hello. And if some bool is false, it's going to give me back, oh, I messed up. Some bool equals false. I messed up. False is kite. Try that again. Some bool. So let's say some bool is false. So now that some bool is false, it gives me back goodbye. And if some bool was true, it gives me back hello. So depending on which one of these functions some bool is, if it's the true function, it selects the first thing. If it's the false function, it selects the second thing. So we can use it just like a ternary. It's the same idea. use the bool to select between two possibilities. And we can assign it. We can say like, you know what, define some bool to be the true function or define some bool to be the false function. So we have data. Our variables can stand for functions and our functions can be useful. So yeah, true is the kestrel, false is the kite. Now, that's kind of interesting, but of course we have a lot more in Boolean logic that we can do. For instance, the not function. Remember, not true should return false, and not false should return true. Well, in Lambda Calculus, we don't have exclamation marks, points as symbols. So we have to get rid of that. We're going to replace it with a function. We're going to call it the not function. It's a function on one argument. It takes a bool and returns a bool. And whatever bool you give it, it has to give you back the other one. Well, remember, the true function is the kestrel and the false function is the kite. So these are the same thing. So the not function, whatever we define it, if you give it the kestrel, it's got to give you back the kite. And if you give it the kite, it's got to give you back the kestrel. But remember, the kestrel and the kite are just functions that operate on their arguments. So the kestrel is a function that returns its first argument, and the kite is a function that returns its second argument. So the kestrel and the kite are very, very similar, but you can get the other one using flip. Remember? So if I flip true, remember, true returns the first argument, false returns the second argument. But if I flip true, the flip function reverses arguments. So now the flip of true is something that returns 2, which is what false does. So the flip of true is false, and the flip of false is true, which means my not function is just flip. That's it. I've already defined it. And I can prove this. Not true is false. How can we know it's false? Because if we give it two things, it gives us the second. Not false is true. And if we give it two things, it gives us the first. Wow. We're doing Boolean logic. And we're doing it without any JavaScript Booleans or JavaScript Boolean operators. We're inventing it from pure scratch. There's another way to do this. You'll see it in the slides. In the interest of time, I'm going to gloss over it. But all it does is use the true and false functions to select their own opposites. So we can write a function like this. We could say not is a function that if you give it either the true or false function, it calls the true function on false and makes it return false. And it calls the false function on true and makes it return true. So we could say not true is false and not false is true. And that works just the same way. We'll not dwell on that, but it's beautiful, and we'll include that. We could do something like this with and as well. I know we're getting very close to time here, but we've got about 5 more minutes, 5 to 10 more minutes. Gonna go really quick. So what about the and function? Well, just think about this. Instead of a double ampersand operator that goes in fixed position, we could say and is a lambda function that takes 2 inputs, right? And is on 2 Booleans. Now we know these Booleans are each either the kestrel or the kite. So we can use one of them. We can say, okay, let's say that this first function, it's going to select between 2 possibilities. Well, this is an and function. So if this first value is false, then we want it to return false, right? But if this first value is false and it's the kestrel kite function that returns the second thing, then all we have to do to make this return false is to plug in a false in the second position. And if this is the true function, that's a function that returns its first argument. And if this thing is true, well, we still have to look at Q to make sure that Q is true. So we can plug Q in there. And what we're saying is for any 2 Booleans, P and Q, P, if it's bad, return bad. If it's good, check what Q is and return Q. And it turns out since if P is false, return false, we could just put a P there instead. So we get this and is PQ, PQP. And takes a P and a Q, and it returns P of P and Q and P. So if we do and true, false, hey, if you and something with a false in it, you get false back. And false and true, the kite is false, still false. And false, still going to be false. But if you and true and true, boom, there's the kestrel. That's our true function. So and true, that gets you what you would expect. Wonderful. You could do the exact same thing with or. You take two functions, you call the function, which returns one of two things. If it's the true function, well, an or can short circuit, so you could just return true right off the bat. And if P is false, you could return whatever Q is because Q might be true. And so you get this PPQ thing, and it looks like or takes a P and a Q, and it returns P of P and Q. And if you or true and false, of course, we know that with or logic, you get true back, which is the K. You or T and P, you still get true. False and true, you still get true. And it's only when you do false and false that finally you get false back. It works, once again, with no built-ins, no JavaScript Boolean operators. There's some fun things you could do here, like notice that variables, the way they simplify in algebra, this is actually similar to the M function. And you could use the M function the same way. This is just a coincidence. This is like not super cool, but look at that. If you use the M function like the OR function, you get true back. Still get true back. Still get true back. And if you do OR of false and false, then you get false. So there's some cool little things here where you discover that some of your expressions yield the same result. And finally, there's this one. This takes in two Booleans. It calls the Boolean on two possible choices. And each of those choices uses the second Boolean Q to select between two possibilities. And what's the final outcome? Well, if P and Q are the same, you get true. If P and Q are the same, you get true. If P and Q are different, you get false. And if P and Q are different, you get false. So if P and Q are the same, you get true. And if they're different, you get false. That is called equality. Boolean equality is when you get a P and a Q, call P on Q of T and F, Q on F and T. And now I can check. Oh, that wasn't what I wanted to do at all. Now you can check. Hey, does true equal true? Yes. True equal false? No. Does false equal false? Yes. Does false equal true? Nope. We've defined equality from scratch using selection. And there's ways of simplifying this that you can realize that that's a not function and that was redundant and this thing condenses. Call me. There we go. And we're almost at the end here, but now we have enough that built up through logic that we can express interesting real results from mathematics and logic, such as De Morgan's laws, which say not P and Q is always going to be the same as not P or not Q. And here it is in symbolic logic, and here it is in JavaScript, and here it is using these names for Lambda calculus functions that we've developed. And we can prove this by replacing each of those names with its actual Lambda calculus syntax. And we can say that it is always going to be equal, that not of P and Q is the same as ORing not P and not Q. Wow. That was a quick spin. You may be dizzy. You may have gotten lost the thread at some point, but I hope you got the flavor. The flavor being that just from pure functions with no built-ins, no primitives, no syntax, no nothing, we can invent Booleans and Boolean logic. And it turns out you can keep doing this. And in part 2 of my talk, I invent numbers from pure scratch without using a single JavaScript number. Arithmetic on numbers like addition and multiplication and exponentiation. Even data structures, things like tuples where you have a first position and a second position, you can extract bits of the tuple, and then you can start nesting tuples, which gives you linked lists. Type systems, Once you have tuples, you can couple every value with an integer, and the integer is a symbol that represents its type. So now you could do checks before you do any operations and check that the type is correct. So you get runtime type checking inside of Lambda Calculus. And even recursion. Recursion is not part of the base Lambda Calculus. It is not part of the rules of how you simplify expressions in Lambda Calculus. But there is a function inside of Lambda Calculus that reinvents recursion from scratch in a language which has no explicit recursion. Can't fit it all in today. We're already practically over time. I'm very sorry, but you're just going to have to go watch part 2 on YouTube somewhere. We're now into the conclusion. There's a couple more slides here, but I really just want to hit on some themes. The really exciting part of this is the way combinators combine with each other to create new stuff. From a bunch of simple axiomatic primitives, you can start slinging things around and quickly building up a complex system just through combination, not even through like wiring it internally and writing the logic. You just combine things. So how many of these functions, these axioms, do you need to invent the whole world? How many do you need to have the complete system? Is it 20? Do you need 20 of these starting functions? 10? 5? Well, what about just 2? These are 2 called S and K. You can define them from scratch using something like Lambda Calculus or just by writing what they do to other variables. And this is called the SK combinator calculus, or sometimes the SKI combinator calculus. But it turns out you don't need I, because S of K and something just gives you I. Combinators in action. Using just those 2 functions, you get the identity function. You invent it. I didn't show you the video. It's in my part 2 talk. But how do we make it using just S and K? Like this. It's easy. Okay, obviously this is crazy, right? This is so dense, but you can do it. It is possible. And actually, you don't need to. You only need one. This function can invent every other function and can compute anything computable. Every program ever written can be expressed in terms of this single function called iota. If you call iota on iota, you get the identity function. If you call iota of iota of iota of iota, you get the k function. And if you do one more, you get the s function. And since s and k can do everything, iota can do everything. Oh my goodness. So why? What was the point of this entire talk? Why are we here now, an hour and 7 minutes later? Well, to me, this is just fun, right? I studied math undergrad. I wasn't the best at it, but I did it. And it's, that was why Smulyan wrote his book. It's a bunch of fun games and puzzles. It's a great thinking exercise. It's a great mental workout. You start to learn to think in terms of functions and combinators and to get a lot of practice for that. And that has practical value because functional programming languages, at their core, their DNA is Lambda Calculus. Now, they do a whole lot more. They've got type systems and data, and they can call down to the machine and do floating point math and all sorts of stuff. But they also use a lot of these ideas, first class functions, currying, high order functions, combinators, etc. And so this is great practice for that. And it feeds into how you think that way with symbol replacement. That's the idea, variable replacement. Substitution, it's the source of all this. But finally, it's also just art for art's sake. Like, I just think this is a wonderful, beautiful little thing, which is why I get excited about math. And I hope you do too. There's a bunch of slides in here. We'll share it out. You can see all this stuff. You could go watch part 2. And of course, I couldn't possibly end this without mentioning the most famous combinator of all time. It's called the Y combinator, and it's the function that invents recursion. You can't use it in JavaScript because it's an infinite loop, but you can use a version of it called the Z combinator. That's the talk. I really am grateful for everyone who stayed the extra 10 minutes. And yeah, thanks so much. I'm happy to take any questions. I'm also happy to let people go because we went a little over. I apologize. So yeah, what's up?
Any questions? I think you got all of us. You killed us.
I think what?
I think you killed us.
Oh, sure. Too much.
We've got one question.
So, since we like to do JavaScript, and JavaScript is inherited from like Scheme and Lisp, is there like a different, a theoretical difference between like how Lisp is constructed and how Lambda Calculus is like his Lisp come directly from Lambda Calculus, or is it like some kind of concurrent way of?
Just because of the volume, I could only hear about half of that, but if I understand correctly, you're asking a comparison of Lisp and JavaScript with respect to Lambda Calculus?
Yeah, less than Lambda Calculus.
Yeah, I think the question is Lisp equivalent to Lambda Calculus, or is it something else?
Yes, Lisp processors, the way they were written, are often cited as like some of the world's first practical Lambda calculi in a computer language. I don't know Lisp myself. I've started learning Scheme recently, just out of interest, and it is my understanding, although I could be wrong, and I will gladly accept correction, that Lisps are essentially Lambda calculus in another form, just like many other functional programming languages like Haskell have at their core the concept of Lambda calculus.
Okay, thank you very much, Gabriel. We've got to end the conference now, but it was a real pleasure to have you.
Thank you. Thank you, everybody. Really glad I could come.